Hello everyone, my name is Vakas and I'm going to talk about our recent project on video spatial temporal action localization, and this is a joint work with my advisor Dr. Mubarak Shah. The main motivation for this project is that the bounding box annotations are very crucial to computer vision development of several computer vision applications like segmentation, tracking and object detection. However, in contrast to object detection, spatial temporal action localization is much more harder problem, and it requires several hours of human efforts and is subject to the human biases and require expensive the annotators interfaces. So what we want to do is that we want to achieve automatic spatial temporal action localization with as minimum supervision as possible. And in this project we are interested in where is the action instead of what is the action. So what I mean to say here is that given the video and the video level labels, we want to put and which is undergoing a complex spatial temporal action, and what we want to do is that we using only single video we want to and using video level labels we want to put spatial temporal bounding box across an actor. So this is a quite active area of research, and there have been a significant amount of work related to that in the literature. For example, there have been object localization or action localization and object segmentation using the negative videos. So negative videos means that the videos that don't have the labels for the videos we are interested in. Then there is also a weakly supervised object co-localization, in which we have the multiple videos and or multiple images, and we want to localize the common pattern or the common object across the video. There have been a recent work for unsupervised object localization. What they did is that they even don't assume the the image level labels, and they come up with a method to obtain the common object across the images. There have been a significant amount of work for using the videos and images jointly. For example, there have been recent works where people have used have trained an object detector using the videos and vice versa. They have trained the object detector from the images and tested over the videos. And also there have been a recent work for video summarization using the images. So in our problem we want to localize action using localize action in the videos. So our straightforward approach would be to take one of this method and then extend it from the 2D to 3D, from object localization to action localization. But the problem is that multiple processing of the multiple videos is very hard for localization, and furthermore, but if we don't have the multiple videos of the same action. So one of our key observation here is that the action images captures key poses, canonical viewpoints and the important instances of the action. So for example, if we look at the images which are downloaded from the Google using the weightlifting, so they carry the very useful information about an action, the gist of the action, and they capture the discriminative poses and the key instances in an action, and give us a very useful information about how the action looks like. Similarly, the action like swinging side angle, we can look at that these images capture the particular articulation of the specific action. So our key idea is that the spatial temporal locations in a video which captures these key poses can be a good candidate locations to localize an action. So what we mean to say that, for example, given a video which has this person performing the action kicking, and we want to basically put a special temporal bounding box across an actor, if you see that these locations has across the video, they have the common the patterns in the images. And so what we want to do is that we want to leverage that information from the images to the videos to get the spatial temporal action localization. So this problem is, although it looks appealing, but this has several problems or several challenges. So first of all, in the videos, we have large number of candidate action locations. Then if we want to use the images from the Google or some website are already noisy. And also how we want to get, how we can get the bounding boxes in an images, and furthermore, how actually we use the images to localize a different domain, which is the videos, to localize the action in the videos. And furthermore, if we want to apply our method on the untrimmed videos, so for the recent challenging data set like Thomas, they don't have the special temporal annotations available to validate any special temporal localization method. So what we did is that in this paper we propose a very simple but effective approach to do a special temporal action localization. So given the video, we obtain the several action proposals from in each video. Then given the image level label, the video level labels, we actually downloaded the image from the Google, and then we removed the noisy images from this collection using the random walk, and then we obtain action proposals in the images, and finally we reuse these action proposals in the images to rank the action proposals in the video and get the most probable location in the video which contains this action, which contains the specific action we are looking for. And now I'm going to go into the details of each of the average step briefly. So first of all, we want to our first challenge was that how we can obtain the good candidate locations in the video, because there can be hundreds or thousands of locations in the video. So what we did is that we use a supervoxel based video action proposal method. We get the candidate locations in the video, but still there are significant amount of the proposals in the video. So what we did is that we use non-maximal suppression over the optical flow to remove some of the noisy and the background of the camera generated action proposals. So here I'm showing you a couple of the action proposals. So the colors is chosen randomly, and the three boxes here is basically showing us the three special temporal location in the video which can contain an action. So given the action proposal we have, we download the images from the Google using the image level, using the video level label, and we once we get the images, we remove the noisy images using the random walk. So what exactly we did is that we basically compute VGG features from each of the image, and then we basically this is basically shows us the transition probability from the each node, which is I and image I and J to image J, and this is a 5% the VGG factors, VGG features, and we use basically VGG 16. And then this is basically a relevance score of the node J at the iteration K, and this is the relevance score of the node relevance score of the node I from of all the nodes in the previous iteration, and this is a transition probability from the node I to node J, and this is in the starting probability. So in this way we are able to remove the significant amount of the images which are noisy. As you can imagine that even the images are pure, even if we get in ideal cases, even if we are able to get the 100% pure images, I mean clean images which don't have any outliers, but still they have they are captured in the very different scenarios, so they have the very different backgrounds. So what we want to do is that we want to get rid of these backgrounds so that we can focus on the area which actually contains an action and use that to obtain localization in our videos. So what we did is that we built on the recent state-of-the-art method for unsupervised action proposals in the images. So we extract a lot of region proposals in each image, and then we find the similar images across images First of all, the similar images using the nearest neighbor on the gist feature space, which is global feature, and then we basically find the common regions across the multiple images. So common region in the images of in the action images is action itself. So for example, these are the couple of the examples where we localize the action in the images. So these two random boxes, boxes shows the action proposals in the images, and these two actions are like a baseball pitch and the golf swing and tennis swing, and these two examples are actually the outliers or the noisy examples. So here basically this method fails because we have the person is very small and not in the center and not salient, and here we have the problem because of the clutter background. So but overall we observe this method works pretty well to localize action in the images. So now we have the action proposals in the videos and we have action proposals in the images. So what we do is that we reconstruct action proposals in the images, in the videos, using the linear combination of the action proposals in the images using sparse representation. So consider video V where we have the k number of action proposals. So what we did is that we extract the VGG16 features from each of the key frames, and this phi basically represents a matrix. So D is a dimension of the feature and N is the number of the key frames in the video. And then we have this matrix epsilon basically shows us the vertical concatenation of the VGG features in all the images. So so basically we have the multiple action proposals in the images and we make a kind of dictionary out of that, and this is basically this matrix which is epsilon basically shows us all the action proposals in the images. So what we did is that we try to reconstruct the video proposals, which is this one. This basically represents one video proposal, and it is a matrix which contains the vertical concatenation of the keyframes of the VGG features, and this is all the images proposals and the vertical concatenation of all the image proposals. So we want to find to minimize this error and this reconstruction error. So, but we know that not all the images are useful because there are definitely some noisy, and also the image proposal method may have some problem. So we basically introduce sparsity. So this basically, the second term basically introduce sparsity to so that some of the values in the C matrix can become 0. Furthermore, you might have noticed that this matrix is basically keyframes of one proposal, which means that they have they are kind of extracted from the consecutive frames, which means that they have the temporal consistency in a matrix. So these features in this matrix are basically have some kind of temporal relationship. So in order to enforce that kind of relationship, in order to preserve that relationship, what we did is that we basically enforce that consistency in this coefficient matrix. So basically what we did is that we want to make sure that the corresponding column of the matrix, which are basically corresponding to each of the frames in the video, should be consistent. So how we did is that we basically compute the mean of the matrix, and then we try to get mean of the matrix, which is one column, and then we concatenate it into the same size as the matrix C, and try to minimize the distance of all the columns from that mean. So basically in this way we enforce the consistency across the columns of the matrix C. So, so using this, we basically get the reconstruction error for each of the proposal, and for example, assume that can be denoted as RP. So, what we did is that we have the reconstruction error for each image, and then we have the motion score. So motion score is nothing but the normalized optical flow derivatives that we have in the very first step, and we use that as in addition to the reconstruction error. So this is our overall probability of each of the proposals. So this is a reconstruction score. Basically this is not an error, because one minus error is the score, and this is a motion score. So we normalize it both of them separately from 0 to 1 and add them together to find the final probability of each of the proposal. So this is the higher the proposal, higher the score, higher the probability that these candidate locations contain an action. So our method is quite generic, so it can be equally applicable to the untrimmed videos. So we go ahead and apply it over the untrimmed videos. So basically we divide all the videos into shots, and then we compute action proposals in each of the shot, and finally we discover the low reconstruction error proposals in each of the shot and use them as a localization in the untrimmed videos. So we did extensive experiments on the trimmed as well as untrimmed dataset. So for the trimmed dataset, we use user sports, which contains 10 human actions, and for the untrimmed also Thomas 13, which contains 24 human actions, and it contains 3207 videos. As for untrimmed videos, we basically use the 4 actions from the Thomas 14, and this is the actions we annotated ourselves. So, first of all, I'm going to show you some of the experimental qualitative results for the trimmed action research. So, to avoid confusion, I just want to tell you that the bounding boxes which I'm going to show you over the videos, the green will show the proposed method, and the green and the red will show the ground truth, which is manually drawn by the person. So here I'm showing you the experimental results for the diving, golf swing, and kicking, and you can see that the person is going through the huge articulation, and a lot of camera motion is here, but still our method is able to localize action quite well over the time, and it captures all the articulations. And also, for example, the motion here in the kicking is quite fast, but we're still able to capture the location which contain an action. So here are some more videos which are from the running, skateboarding, and horse riding. So the running is basically, as you can see, that again the motion is quite fast, and there's a lot of accretion, but still we are able to localize the action quite well. And here the person undergoing the scale change from very small to very large, but still and we are able to perform pretty well for these localization tasks. Here are some more examples of walking, swinging side, and lifting. And here you can see that in the swinging, for example, in the swinging side, the person is going through a drop motion, and very small size and the huge articulation in shape, but still we are able to localize action quite well across the whole video. And here are some of the more examples from the same data set, from the swinging. So now I'm going to show you some of the quantitative results. So for the user sports, we compared it with the 2-week recently proposed weekly supervised localization methods. So for the crane, we obtained 65% localization accuracy for the user sports, and we used the threshold of 20% following the lot of recent work for action localization. For negative mining, we get 63%, but for our method, we outperformed significantly from both of the baseline and get the 92% localization accuracy. So as you have observed that our method has several components. So we have analyzed each of the component and to see how much it contribute to the final accuracy. So we used all the images without noise removal, get 65%, and then after noise removal we get 68% localization accuracy, which means that removing the noise from the images helps. Furthermore, when we remove all the distracting background, which means that we obtain action proposals in images and try to reconstruct video proposals, we get 83% localization accuracy. Then we use these image proposals along with the and the constraints, the sparsity and consistency, we get further 5% improvement in localization accuracy. And furthermore, when we add motion information, which is also very crucial for any action, we get the 92% localization accuracy. So as you can see that each of the component is actually contributing toward the localization accuracy that the final we get. Here I'm showing you the quantitative results for user sports across the different threshold, and you can see that although we perform pretty well at the lower threshold, however our also the localization accuracy is a high threshold like 0.5 and 0.6 is also reasonable. And however, as you might have think that the localization accuracy decreases with the increasing threshold. And here I'm showing the same results for the Thomas 13, and as you can see that all of the patterns of the results the numbers actually are lower for the users for Thomas 13 as compared to user sports, but this is mainly due to the complexity of this data set, and the Thomas 13 is much bigger than the user sports. Now I'm going to talk about show you some quantitative and qualitative results for untrimmed action data sets. So as we discussed before, we have the problem of a lack of special temporal annotation for Thomas. So but we plan to release is that the annotation of 35,000 frames of 4 actions from the Thomas 13, that and we will release these annotations along with the publication of the paper. So again, I'm going to first show you the qualitative results, and the green bounding box in the video will show the proposed method, and the red bounding box will show the ground truth. So here I'm going to show you the tennis swing, the video, and the person in the initially he will, since it's the untrimmed video, so the person is not completely performing action over the whole video. So in the start he will teach how to perform an action, and then he performs the action, which is a tennis swing, multiple times, and we are able to localize actions when it is performing, and also as well as the multiple times. So, and here in the bottom, I'm showing you the localization accuracy for the localization qualitative results for the throw disc, and you can see that the person actually he performs an action, but then he stops action, and in the upper case initially don't perform an action, then perform action multiple times, and in the both cases we are able to localize action quite well. So in order to quantitatively evaluate our localization accuracy on the untrimmed videos, we basically use the standard false positive rate and true positive rate. So the x-axis shows the false positive rate, and the y-axis shows the true positive rate. So this curve shows the negative mining, the curve that we got for the negative mining, and this is the yellow curve shown for the crane, and this is our method, which again significantly perform better than the two baselines. So in conclusion, what we have I have shown you is that we have shown the feasibility of web images for spatial temporal action localization, and we have shown that that it is possible to construct the video proposals using the image proposals, and using some like sparsity constraint and consistency constraint, and we can able to get very good localization accuracy in the trimmed as well as untrimmed videos. We will release the annotation of 35,000 frames of the Thomas 14 for the 4 actions, and we believe that this is a very important problem and a very challenging problem, and so in order to facilitate further research in this direction, we will release code, web images and annotation on our web page soon. Thank you very much.